we're going to talk about measures of variability. So what you're going to see with these three data sets is that mean is insufficient. So we're trying to summarize an entire data set, and so we pick the middle of the data set. But that is not good enough. I'm going to show you why in this example. I'm going to find the mean for each of these data sets. Okay. So we're going to use our built-in formula for mean, which is average. And we already know that the average of 10 fives is going to be 5. But when I go to find the average, actually, oops, I can highlight both of these and copy and copy. Now you might think, oh, I copied that wrong, but I didn't. This is actually finding the mean of this data set, and this one is finding the mean of this data set. It's just that they all have a mean of 5. So clearly, having the mean describe the entire data set is incomplete in this case. So what we want to do instead, sorry, I get really caught up in the aesthetics here. So I just want to make sure we can read this clearly. Okay. So what we want to do is we want another number to help us describe a data set, and that's the spread or the variability of the data in the data set. Now, what I'm going to do really quickly is I'm going to show you what graphically these look like with a histogram. So again, the built-in auto feature of Excel has let us down. I'm going to do a bin width of 0.9. And we're still going to see, okay, so, all right, I get it here. So I wish it would let us go a little bit higher, but it's not going to let us do that. Can I go? There's no way to make this go down. Yeah. All right, so what I want you to imagine is I want you to imagine when I go to create the histogram here, is, again, this should be the same. This should be symmetric because it's set up that way, but because this is including 4.9, it's not going to happen. So what I'm going to do is I'm going to make the bin width be 0.9, and here we go. So you can see this data is a little bit more spread out. In the previous one, the bar that had the 5 in it would have just been all the way up to 10. It would have been 10 tall. It actually has 0 variation in it in that data set. But this is data set 2. Now let's compare that with data set 3. Again, Excel letting me down here. We're going to make sure we know this is data set 3. And what I'm going to do is, again, make the bin width 0.9. And 0.9 is what we need to do to make sure that that first bin only contains one value. So this contains 2, 3, 4, 5, 6, 7, 8. Okay, and this contains, all right, 3, 4, 5, 6, 7. So you can see this data set 3 is the most spread out. Data set 2 is spread out, but not that much. And data set 1 is not spread out at all. It's a single bar over top of 5. And so how do we describe the variability? So what the standard deviation does is it actually finds the average distance of every point from the mean. So let me show you how this works. And I'm going to do this with data set 2. I'm going to reference this cell and just copy my data. Okay, so we know that the mean is 5 and it's here. So if I wanted to find the distance of every value from the mean, I would take this data point and subtract the mean from it. I'm going to lock the reference to the mean because I want to subtract the mean from every data point. So this is the distance of every data point from the mean. These 4 values are the mean, so they have 0 distance from the mean. And as we get farther from the mean, we have more distance. Some are negative, some are positive. What happens is if I average these distances, if I just do a straight up average, what happens is the negative values on one side cancel out the positive values on the other side. And so the average distance ends up being 0. So that's not an accurate picture of what's happening here. There's definitely spread. It shouldn't be 0. So what we actually do is we take that distance from the mean and we square it so that all of the means are positive, or all the distances from the mean are positive. So we're going to square all the distances from the mean. Then we find the average. I actually said I wanted to find the average. And then we square root it because we squared everything, so we're going to square root it. And so that becomes my standard deviation. And if we actually calculate the standard deviation, it's going to be a formula, standard deviation. Now, depending on whether it's a population or a sample, is going to determine the value of the standard deviation. And you can see this matches up perfectly with what I did. If I wanted to find the sample standard deviation, it's going to differ a little bit. And the difference in the calculation here would be, instead of averaging with the average formula, I would sum up all the values, and then I would divide by the number of values minus 1. So this data set has 10 values, so I would divide by 9. And you can see when I square root that value, I get exactly the same thing as the built-in formula. So that's the big difference between the population and the sample standard deviation. I will try to be as clear as I possibly can whether the data you're looking at is a sample or a population. When we talk about the exam scores, if our population of interest is anyone taking that exam, then the exam scores we had were a sample. But with the MLB teams from 2021, that was all of the data that we had from that year. So the MLB teams would be a population. Now, if you end up treating everything as a sample, you're probably 9 out of 10 times you're doing the right thing. Okay? And it won't be a huge thing if you mess up the fact that it's a sample instead of a population. That's okay. That's not my main concern. My main concern is that we can describe the variability of these data sets. And so we have our standard deviation. And so my standard deviation, there's a built-in formula for this. So I don't have to go through a ton of work. I'm just going to do stdev.s for sample. And I'm going to find the standard deviation of my first data set. It's 0. Weird. I knew that was going to happen. And then I'll find it for the second data set and the third data set. So notice, the standard deviation gets larger the more spread out the data are. Now, when the standard deviation gets much bigger than compared to the mean. So if we just think about what 1/3 of the mean would be, it's about 1.667. As long as our standard deviation stays under that, then we can say, you know what, the mean is probably a reliable measure of center. You know how we talked about what's the best measure of center? Is it the mean or the median? What it ends up being is if our data is skewed, we want to use the median and not the mean. If our data is symmetric, then we want to use the mean and not median, because the mean and the median should be close to one another anyway, so why not use the mean if they're very close? But the larger my standard deviation gets, the less reliable that measure of center really is. And in a data set like this that's perfectly symmetric with a hole in the middle of it, we'd probably just want to graph this so people could see this looks bimodal. And so it looks like I would want to describe this with two numbers. There's a center of this cluster, and then there's a center of this cluster, and I might want to describe those with two different numbers. But most of our data is going to look more like this, something that's normally distributed, symmetric. And so this standard deviation is less than 1/3 of the mean, and so I would say that's a very valid mean to describe the center of this distribution. Since the formula is built into Excel, there's not a whole lot that you have to do to calculate it. You're just going to use the built-in formula if you have the original data. But let's say you didn't and you had some grouped data. How would you find the standard deviation? That is not something that we're going to cover in this class. If you need to know that information, I will give it to you. Well, that's all for this video. I will see you in the next one.